theorem of Morse is that every m-dimensional manifold admits a Morse function. Okay, so a justification, which is more an idea of the proof without verifying, is that we know by Whitney's embedding theorem that we can embed our manifold into, say, S2x1. And then we take the metric from the subspace metric, we include it, and we look at the norm associated to that, and we define a function so with subspace metric, define L sub x from M to the real line, which just takes the point y in the manifold and maps it to the square separation from x to y. And it turns out that Lx is Morse for almost all points. When I say almost all, I mean this in the rigorous sense that it's up to measure 0 offset. Okay, so not only do we know that there's a lot of Morse functions, but we can also, we know how to find one. In fact, so these might form some of the questions from this lecture, but you can show that Morse functions are open in a set of C2 functions. So if you find one that doesn't happen to be Morse, you perturb it slightly and you will get a Morse function. So I said dense. I mean dense and also open. It's dense in continuous functions and it's open in C2. Okay, so thus, given equilibordism, we can find a Morse function and this gives us handle decomposition. But clearly, this handle decomposition is not unique. We had a huge amount of choice in choosing a Morse function, and you don't necessarily get the same handle structure. So it's not unique. So Andrew mentioned in his lecture about how you can have an I handle cancelling with an I plus 1 handle, for example. Or you can slide handles around, or you can trade handles up using two cancellations. So the decomposition is highly non-unique. So I'll give an example of some handle cancellations. So an I handle can cancel an I plus 1 handle if the intersection of the attaching sphere of the I plus 1 handle with the belt sphere of the I handle is a single point. Attaching sphere with the I's belt sphere is a single point. So, two examples. So if we take D2 and we attach a 1 handle, so here's D2, and might as well stick to my colour scheme. So here's a framed S0. So we've attached a 1 handle via this red S0, and so this is going to be our I is 1 in this case, and we're going to look at the intersection of the belt sphere with the attaching sphere of the 2 handle. So we now attach a 2 handle, and for it to cancel the 1 handle, it has to intersect one of these points. So namely what we do is we attach to this entire circle so this is our D2 cross D0, I suppose, and fill that in, and this, the result of attaching this handle is to get D2 back again. So this, patching this on has cancelled the 1 handle. And again, practically the same picture for D3. I should really do S1 to make this different, S1 but never mind. So we have this framed embedding, there's a 1 handle, and now the belt sphere is this S1 here. And so to cancel this, we just need to attach around this handle, so that the intersection here is just this single point. Okay, so there's one or two more things I might like to say. let's write this quickly. So we've already shown that we can find a handle decomposition, but in particular, what we can do is, if we have one handle attached on top of another, we can always, it turns out, slide an I handle off of a J handle if I is less than J. So what this means is we can build up a handle decomposition where we have, say, one handles all attached at the same time, then two handles, and then up to M, I guess, handles at the top. So we can have them all lined up like this, just by sliding handles off of each other. So the theorem is every, let's see, M plus 1 dimensional cobordism admits such a handle decomposition H here stands for handle, H ij plus 1 stands for handle, an ij plus 1 handle. So all I'm saying here is that we can attach them in order, like I was saying in the picture. And the justification is this sliding argument. But what I want to point out is that there's a nice Morse theory analog of being able to slide handles off of each other, and that is what's called the existence of a self-indexing Morse function. So we say a Morse function is self-indexing if so F is self-indexing if for all critical points, let's say X, the value of that critical point is the index of the critical point. So F of X equals the index of X. So in particular, if we choose a self-indexing Morse function, then think about the ascending cobordism. We go up as we hit level 1, we attach lots of index 1. We have a lot of index 1 critical points, so we get a lot of 1 handles. And then we ascend to height 2, at which point we attach all the 2 handles, and so on and so forth up to the top. So this Morse function gives you this this nice decomposition where you have all 1 handles attached, then all the 2, then all up to M.